In this video, we're going to look at a couple examples involving logistic growth. And I want to introduce this just by comparing it to exponential growth, which you've seen in previous math courses, and we've even seen a little bit in calculus this year. In exponential growth, we assume that the rate of increase or decrease of a population, an amount of money, and a number of bacteria, whatever we're modeling by the situation, we're assuming that its growth is directly proportional to the size of the population. And so we end up with this differential equation that the rate of growth is some growth constant times the population. And that results in an exponential growth graph that looks something like this. And, this model works for some scenarios, but in many cases, the potential for growth has a limiting value. And when that's the case, that's when we have logistic growth. A logistic growth differential equation looks like this, where the rate of increase is directly proportional to both the current population as well as the remaining population or the remaining potential for growth. L here stands for a limit, or it's also sometimes called the carrying capacity. And P, of course, is the population. And so you can see this graph here, this graph models P of T. And it starts out, if we just look at the first part of the graph, it looks exponential. But then there comes a time when the concavity of our curve changes. It continues to grow, but it just approaches this limiting value. And the limiting value could be because of, a limited number of resources where the population cannot grow beyond a certain level. It could be if we're talking about the spread of a disease or a rumor, that we're just reaching the point where everyone in the population has either heard the rumor or has been exposed to the disease. And so logistic growth just gives us a way to model the growth of an exponential type situation that is eventually going to reach some kind of carrying capacity, some kind of limit. So let's look at an example here. The population P of T of fish in a lake satisfies the logistic differential equation dP dt equal to 3p minus p squared over 6,000, where t is measured in years and p of 0 equals 4,000. So our initial population of fish in this lake is 4,000. So our first question here is, first of all, identify the limit. As time goes to infinity, what is the limit of our population? This question is asking here, what is that carrying capacity? We have a lake here, we're stocking it with fish. How many fish can the lake actually handle? So in order to calculate that, we're going to take our differential equation, dP dt is equal to 3p minus p squared over 6,000. In order to identify that carrying capacity, I need to get this differential equation in the form that I showed you previously, K times P times L minus P. What is really important here is that this P is does not have a coefficient on it right here. And so as we can see in our example, we've got a coefficient of 1 over 6,000 on this p squared term. So we're going to factor out here, we're going to factor out a p. We're also going to factor out the 1 over 6,000. So this is going to be equal to 1 over 6,000 p times, so if I divide 3 by 1 over 6,000, That's going to give me 18,000 minus, and then here I'm left with P. Whenever we are trying to get a logistic differential equation into the form where we can identify the limit, that's what you want right there, is a P with no coefficient on it. And once we get it here, then we can easily identify the carrying capacity. Remember, this is our L value or our carrying capacity. And so the limit as time goes to infinity is going to be equal to 18,000. So our next question, what is the range of the solution curve? Well, we've identified the limit, the highest value, which is going to be 18,000, or it's going to approach 18,000. And we said here in the beginning that our number of fish is going to start at 4,000. And if you remember the graph I drew previously, our curve is always increasing. So our range is from 4,000, that's where we're starting, to 18,000. And we're just going to put an open parentheses on that because we're going to approach 18,000. As time goes to infinity, the population of fish is going to approach 18,000. All right, so then for question C here, for what values of P is the solution curve increasing or decreasing? Justify your answer. So now we're doing a little A-B review. Whenever a curve is increasing or decreasing, remember that's, we want to think about the derivative, and when is the derivative positive, when is the derivative negative. So my derivative is dp dt is equal to, I'm going to write both forms that we have here. And keeping in mind the range here, 4,000 to 18,000, let's just think about that. If I plug in 4,000 for both of these P's, this outside value here is going to be positive, and in here would also be positive. And in fact, any number up to 18,000, the expression here, 18,000 minus P, is going to remain positive. As long as we stick within our range here, this is going to be positive. And so we're going to say that this expression is always greater than 0 and never negative. And so that means that P is always increasing. So then we know that the curve is always increasing. Let's next look at the concavity of the curve. For what values of P is the solution curve concave up or concave down? Justify your answer. So again, I'm going to write, let's start with our dp dt equal to 3p minus p squared over 6,000. If I'm going to answer a question about concavity, hopefully you remember that means we need the second derivative. And so this version of our differential equation, I think, is going to serve us better to find the second derivative. Notice that we are taking a derivative with respect to time. And so when I take the derivative of 3p, that's going to be 3, but I have to multiply times dp dt because p is not t. We have to do the chain rule there, an implicit differentiation. Minus, if I take this derivative, 2p over 6,000, again, times dp dt. So then if I factor out that dp dt, I'm going to make that p over 3,000. And so if I'm going to find when my second derivative here is positive or negative, I need to find when it's equal to 0. Now, normally we would substitute back in what dp dt is, But for this particular problem, I'm just going to go ahead and set this equal to 0. And remember that we said previously for the particular range that we're talking about in this scenario, dp/dt is always going to be positive. And so it doesn't really matter what it is because it's not going to equal 0. We've already stated that it's always positive. So I'm going to take this part, 3 minus p over 3,000. That could equal 0. So P is equal to 9,000. So at that point, when P is 9,000, that means that the second derivative is equal to 0. And so what we need to look for now is when is it positive, when is it negative? When is the solution curve, when is the second derivative positive or negative, which will tell us when the solution curve is concave up or concave down. So if I pick a number over on this side of 9,000, like 8,000, and I plug it in here, 8,000 divided by 3,000, I don't know exactly what that is, but I know it's smaller than 3. And so this is still going to be positive. My dp/dt is always positive, and so a positive times a positive is positive. If I pick a number bigger than 9,000, say like 10,000, 10,000 divided by 3 is going to be bigger than 3, which is going to make this factor turn out negative. And if I multiply a negative times a positive, that's negative. And so I've kind of filled up my space here. Let's see, I'm going to switch to a different color and I can write the answer. So we're going to be concave up all the way up to 9,000. And remember, we're not starting at 0 here. This is starting at 4,000. That's our lowest value here. And then our highest value is going to be 18,000. So we're concave up from 4,000 to 9,000. And concave down here where it's negative from 9,000 to 18,000. Next part, does the solution curve have an inflection point? Justify your answer. Well, we've really kind of already done that because we found, remember, inflection point is where the second derivative is equal to 0 and changes signs. And that's exactly what we just did in the previous part. So yes, P of t has an inflection point at P equal to 9,000. Now this is a little bit weird because normally we are used to writing at an independent variable time at like t equal to some number of days or years or whatever. But in this situation, this is all based on a P value because that's what we solved for up here. We got P equal to 9,000. That's when we have the inflection point. P is equal to 9,000 because the second derivative equals 0 and changes signs. And so based on all of that information, let's just sketch a quick graph of P of t. So first of all, we know that our limit is 18,000. And let's see, 4, 8, 12, 16. I'm marking this off in 4,000s. So 18,000 would be about right here. It's going to be a horizontal asymptote for our graph. We know that we're starting when time is 0. We're starting here at 4,000. That's our initial value. And we do know that the curve is always going to increase. It's going to approach that carrying capacity of 18,000. And the other thing we know is that we have an inflection point at 9,000. So 9,000, let's see, P equal to 9,000. I probably should label my axes. P of t and t. So 9,000 is probably about right here. I'm just going to put an inflection point right here. So we're going to be concave up to that point and then concave down until we reach the carrying capacity. And there you have the logistic curve. Now for our second example, notice that we're starting out with the same differential equation. Exact same situation here, except that our initial population is 10,000. So we're going to look and see what difference does that make. Our differential equation is still going to be equal to 1 over 6,000 p times 18,000 minus p. And so our limit is still the same. That has not changed. But we are changing the range here because now we're starting at 10,000 and only going up to 18,000. For part C, for what values is the solution curve increasing, decreasing, justify your answer. Our equation up here, our differential equation hasn't changed. It's still always positive. And so we're just going to say dp dt is still going to be greater than 0 always for this range from 10,000 to 18,000. Therefore, P of t is increasing, just like we saw before. My little therefore kind of got ugly. Let's fix that. There we go. Okay, so now let's talk about the concavity. Since we are dealing with the same differential equation, our inflection point is still at the same place. In fact, I'll answer this second question first. Does the solution curve have an inflection point? The inflection point, because our second derivative is still, let me find it. It was dp dt times 3 minus p over 3,000. This second derivative is only equal to 0 whenever p is equal to 9,000. That's what we found when we worked this problem previously, because again, this factor is still always positive. But in this case, since my range is starting at 10,000, which is higher than this 9,000, that means for this particular solution curve, we do not have an inflection point. No, because P of 0 is equal to 10,000, and that's greater than the 9,000, which is the inflection point. So then I answered that question first. What that means for our concavity, if you remember before, we had this scenario where it was positive and then negative. If I'm not even starting until I'm at 10,000 here, well, then that means for this solution curve, we are always going to be concave down, because in this scenario, we're not even starting until we get past that inflection point. And so for this one, P of t is concave down. Because our second derivative is less than 0 for our range in this situation, which is 10,000 to 18,000. So second derivative would still be positive, but that's only for population values lower than 9,000. And so since we're greater than 10,000, we're always going to be concave down. And so then for my last question, which apparently did not print here, let's sketch a graph of this curve. What does this one look like? So I'm going to start with the same 4,000, 8,000, 12,000, 16,000. Here's our carrying capacity of 18,000. But in this case, since my starting population is 10,000. We're starting here. And so we're only going to be concave down, but still increasing, so approaching that carrying capacity. And so in this case, that's what our curve would look like because our initial population is beyond the inflection point. Final example, same differential equation, same fish, same lake, except this time our initial population is 20,000. So think about what we're saying there. We have said that dPdt is equal to 1 over 6,000 P times 18,000 minus P. We are saying this is the limit. This is the most fish that this lake can handle. If we initially populate the lake with 20,000 fish, it can only handle 18,000. That's still going to be the carrying capacity. The limit is still 18,000. And so in this case, our solution is 18,000. Our range of the solution curve is from 18,000 to 20,000. And so what's going to be happening here, if you think about it in the real world scenario, the curve is going to have to be decreasing because we're starting out beyond the capacity of the lake. If we consider our differential equation, you can easily see here that if this p-value is greater than 18,000, this factor is going to be negative, which would make this less than 0 for p between 18 and 20,000, which means this curve is decreasing. All right, so then what about the second derivative? Well, our second derivative is dP dt times 3 minus P divided by 3,000. For our particular range, our dP dt, remember we've just said that that's going to be negative. And remember that our range is starting at 18,000 and going to 20,000. So that means this factor, for those values of P, this factor is also negative. And a negative times a negative would be positive. So this is greater than 0 for the range that we're talking about. Therefore, our solution curve is concave up. Because our second derivative is going to always be positive for this range. Does the solution curve have an inflection point? No, because it's always positive. There's no inflection point. So then what does this graph look like? Well, in this case, here's our carrying capacity of 18,000. We're starting at 20,000, and we have discovered that the curve is only decreasing and it's only concave up, which means it's going to look like this. Still approaching that limiting value of 18,000. So let me go back to our original graph here. One of the things that we saw by calculating that second derivative, we found that in our scenario, the inflection point, which is about right here, was at 9,000, and our limit was at 18,000. And if you think about how those two numbers are related to each other, 9,000 is half of 18,000. If you think about this in terms of the capacity of the lake and when the population growth might start slowing down, it should kind of make sense that it would start to slow once we reach that halfway point. And so another thing that we need to remember is that this inflection point is always going to happen at whatever the limit is divided by 2. Halfway to the limit point, that's when our concavity changes. And so in our first example, when our number of fish started at 4,000. We were starting below that inflection point. So we had the exponential growth, which then changed concavity to approach the limiting capacity. Our second example, we started at 10,000 above the inflection point, which means we were always concave down as we approached the limit. In the third example, we started with a number of fish that was above the limit. And so it only decreased down to that carrying capacity of 18,000.